Hello everyone, my name is Mohammad Abdul Hadi and today I'm going to present a paper named on the effectiveness of pre-trained models for API learning. For this paper, my co-authors are Imam Noor Bani Yusuf, Ferdian Thang, Kian Gia Luong, Jiang Lin Jiao, Fatimi Edgeworth, and David Lowe. Developers frequently rely on existing class libraries to implement functionalities by invoking a set of corresponding APIs. Becoming acquainted with an unfamiliar library can be pretty challenging for any developers. It is extremely helpful to identify which APIs to use and in what order developers should actually invoke the API-related methods. Developers can greatly benefit from automatic API usage sequence generation based on natural language queries for building applications in a faster and cleaner manner. Existing approaches either utilize information retrieval model to search for matching API sequences given a query or use RNN-based encoder-decoder to generate API sequences. We want to understand the effectiveness of recent pre-trained transformer-based models or PTMs for the API learning task. These PTMs are trained on large natural language corpora in an unsupervised manner to retain contextual knowledge about the language and have found enormous success in solving similar natural language processing problems. However, the applicability of PTMs has not yet been explored for the API sequence generation task. In our approach, we have also identified two different tokenization approaches that can contribute to a significant boost in PTM's performance for the API sequence generation task. In our study, we are focusing on the deep learning approaches with pre-trained knowledge. For this approach, we have selected the following PTMs to incorporate in our study. These PTMs are BERT, RoBERT, CodeBERT, and PLBERT. Previous studies have already evaluated the performance between information retrieval models and deep learning approaches without the pre-trained knowledge and found that DP API can actually beat the combination of code search and pattern mining based approach for API sequence generation and also beat another information retrieval model which is called SWIM. For this reason, we are actually taking Deep API as our baseline. In our experiment, we have leveraged the dataset provided by Gu et al. Gu et al. Collected around 400,000 Java projects' last snapshots from GitHub. Each of these projects has at least 1 star. After the collection, pairs of API sequence and natural language annotation are extracted by parsing source code files into abstract syntax trees or ASTs using Eclipse's JDT compiler. Gu et al. Finally obtained a database consisting of around 7 million API sequence and natural language annotation pairs. Gu et al. Do not separate the dataset into training, validation, and testing sets specifically, so we randomly selected 10,000 pairs out of 500,000 pairs for the testing set and 7 million for training and validation sets for our pre-trained transformer-based models or PTMs. Here you can see the total workflow of our experiments. With the PTMs, the API sequence generation task is framed as an NL to PL or natural language to programming language translation problem. The PTM's encoder converts a natural language query into a context vector and the respective PTM's decoder leveraged the context vector to generate the corresponding API sequences. All the PTMs are fine-tuned with the same hyperparameter settings, such as the batch size, learning rate, and number of epochs are all the same for all the PTMs. Here we show the result of our first research question, which is, can PTMs yield better performance than the prior approaches? We use Blue Score to evaluate how close are the generated API sequences with the ground truth. Blue Score measures the similarity of a candidate sequence to the reference sequence based on the number of n-gram hits. From Table 3, we can show that most of the off-the-shelf PTMs can actually outperform the Deep API by considerable margin, ranging from 4.09% to 7.39% in terms of Blue Score. The PTM that is pre-trained on natural language corpora, such as RoBERT, requires bigger architecture to outperform the Deep API replication. Before moving on to the research question number 2, we need to understand different tokenization approaches incorporated into our study. In the original tokenization approach shown in figure 1, the decoder tries to learn how to rearrange the tokens to generate valid API names during the fine-tuning. This helps in NLP tasks to make sense of the grammar and different uses of lemma in different contexts, but API names are constant and we want to put more focus on the sequence rather than the API names. We decided to try and modify this tokenization approach, and we proposed tokenization approach 1 or TA1, where the API names will be directly injected into the vocabulary by averaging their corresponding token slices embeddings. But the tokenization approach 1 can introduce a problem, as the subword tokens retain a lot of natural language information from the pre-training corpora. To circumvent the problem, we proposed the second tokenization approach, TA2, where the tokenizer does not break down the API names into subword tokens. These representations are one-hot encoded vectors. Intuitively, tokenization approach 2 can help the decoder to put more focus on the API sequences instead of learning to rearrange the subword tokens. Now let's move on to the results of research question number 2, which is, can different tokenization techniques boost the performance of the PTMs? From table 4, we observe that the tokenization approach 1 or TA1 enhances the performance of the PTMs by a large margin. And from table 5, the results indicate that tokenization approach 2 or TA2 can yield slightly better performance than when using tokenization approach 1. Our tokenization approaches can help PTMs to better learn API sequences. We can understand or observe that both tokenization approach 1 and tokenization approach 2 perform better than the default tokenization, as shown in table 4 and table 5. Preventing the tokenizer from decomposing API names into subword tokens can help improve the PTM's performance if handled properly. At last, to summarize our research, we have applied pre-trained transformer-based models or PTMs for constructing API usage sequences for an API-related natural language query. Thank you everyone. If you have any question, please feel free to reach out to us.